All right, now let's have a look at these problems here. So we're going to try to show, in this case, we were told that we have a bunch of vertices here. So I'm going to go ahead and sketch this out. Now, technically, you don't need to draw a picture, but drawing a picture I find to be very helpful because of the fact that it gives you sort of an idea of what's going on with this figure that you have to draw, and that can give you sort of an idea of where to begin. So here's KATE here. I'm going to go ahead and sketch this out. So we want to show, so the problem here states to show that this is a trapezoid, but it's not isosceles here. Now, if you recall the definition of a trapezoid, our definition of a trapezoid here says that this is a quadrilateral with at least one pair of parallel sides. So I have to show that one pair of sides are parallel. It looks like KA and TE are parallel, so we can demonstrate that using slopes here. So we're going to find the slopes of this. So KA, the slope of KA here, again, we use the slope formula. So we have 7 minus 5 all over 4 minus 1, which in this case is 2 over 3 here. So we know the slope of KA is 2/3 here. We can do the same for ET now. The slope of ET here in this situation, same idea here, going to be negative 1 minus 3 over 1 minus 7. That's minus 4 over minus 6, which becomes positive 2/3 here. And we note this is what we expected to see. We wanted them to be equal slopes here. So we can now mention something like this here. We note that since the slope of KA equals the slope of TE, we know KA is parallel to ET. So note that now we have enough information to show that this has to be a trapezoid. Thus, since KATE has a pair of parallel sides, it is a trapezoid. Now note that if we wanted to show that this was, this uses the inclusive definition. If we wanted to use the exclusive definition, we also would have not only have to show this, we also have to show the other two sides are not parallel to one another, and that's okay. Now we have to show that this is not isosceles. Now remember that an isosceles trapezoid here, one of the hallmarks of an isosceles trapezoid is the legs being congruent here. So now I just have to show that KE and AT are not congruent here. So now I can try to do KE here, so we can do the distance formula. So KE here is going to be 1 minus 1 squared plus 5 minus a negative 1 squared. So that is 0 squared plus 6 squared. The square root of 36 is just 6 here. And now we can do the same thing for AT here. We note that in this situation, AT here is going to be 4 minus 7 all squared plus 7 minus 3 all squared. And that's the square root of negative 3 squared plus 4 squared. And that's the square root of 9 plus 16, which is radical 25, which is 5. And you can see here now, these are not equal, and that's what you wanted to see. So we can now we note that since legs KE and AT are not congruent, the trapezoid is not isosceles. And we can draw our little tombstone here to finish the problem. Okay? All right, now, number 4, in the same idea here. So we have a quadrilateral ABC defined by these. And again, we're going to go ahead and sketch this out here. Okay? So here we have negative 1, 3. So here's A. And again, always a good idea to draw your quadrilaterals. To start here, draw any figure that they ask you to make things a little easier for yourself. So negative 2, negative 2. So it looks like this here. So I'm going to go ahead and sketch this out here. That looks good. That looks good. That looks good. So this looks really odd. So note the problem is saying we want to show that it has perpendicular diagonals and at least one pair of congruent sides, but it is not a parallelogram. Okay, so this is a weird thing here. So the first thing I'm going to do is focus on perpendicular diagonals. So we're going to find the slope of the diagonals here. So AC in this case, again, we're going to use the slope here. So it's going to be 3 minus negative 3 over negative 1 minus 5, which is 6 over minus 6, which is minus 1 here. And now we can find the slope of BD. So we're going to take this one step at a time. So remember, with each phase of the proof here, when you're writing this out, you want to be able, again, the numbers are going to do the heavy lifting for you, but you always want to also explain what your numbers are doing. That makes things a little easier for you. BD here is going to be 4 minus a minus 2 over 4 minus a minus 2, which is 6 over 6, which is 1. And now we know that negative 1 times 1 is just negative 1, which is what you wanted here. So note that we can say since the slopes have a product of -1, we know AC is perpendicular to BD here. So that's the first half. That's the first section done. It has at least one pair of congruent sides. So I'm not sure which pair of sides are congruent here, so I'm just going to have to write these out and see what's going on here. It looks to me that DC and BC are the same, but let's just try it, okay? So we're going to write this out. So we're going to try BC here. So BC, again, we use the distance formula to try to show that this is the case here. So BC here is going to be 4 minus 5 squared plus 4 minus a minus 3 squared. So let's see. That is, let's see, -1 squared plus 7. Oh, sorry, there's a parentheses. 7 squared. So that's the square root of 1 plus 49, which is radical 50 here. Now, I think that is 5 radical 2. Okay, that seems useful. Now, technically, you don't need to write this out here, but I'm going to write it out because, it's sort of been ingrained into me here. CD, we're going to do the same thing. We're going to go ahead and write this out here. So it's going to be 5 minus a minus 2 squared plus -3 minus a minus 2 all squared. Again, we do the same thing here. We just do the arithmetic. You let the arithmetic do the heavy lifting for you. So 5 minus a -2 is 7 squared. And then we have -1 squared. So yet again, it works out really well. We get 49 plus 1, which is radical 50, which is 5 radical 2 here. So thus, BC equals CD. So ABCD has at least one pair of congruent sides. Now, we want to show it's not a parallelogram. So one of the things about parallelograms is that you can find the slopes of these sides here and do this here. Or you may remember things about parallelograms, the opposite sides are congruent here. We already have AB, or we already have BC and CD here. So all I got to do is just show that BC and AD are not the same. Because if BC and AD were the same here, then this might be a parallelogram. But since it's not, if it's not the case here, then we know it's not a parallelogram. So I'm going to go ahead and calculate AD here. And in fact, that actually gives you an advantage of doing everything here. The advantage of writing everything out here is now you can just complete your argument. But I tried to take a shortcut and it didn't work out very well. -1 minus -2 squared plus 3 minus a -2 squared. That's the square root of, it looks like -1 plus 2 is positive 1, so 1 squared plus 3 minus -2 is 5. So 1 squared plus 5 squared is square root of 1 plus 25, which is radical 26. And you can show that this is not equal to 5 times the square root of 2. So we can say that since BC is not equal to AD, we know that BC is not congruent to AD because they have different lengths. ABCD can't be a parallelogram. Since opposite sides of a parallelogram are congruent. And we can end it there.